Good morning. Can you know? Good morning. Oh, yes, now it's on. Good morning, everyone. It's 9, or actually a minute past, but we'll wait 5 minutes, and then just for those that took a late breakfast, and then we start. Okay, so let's wait a couple of minutes more, and then we start. So as you know, this morning we have a full program for this plenary session. We'll have the 2 keynotes from 2 esteemed colleagues, and then at the end we are going to celebrate an anniversary of 100 years. There are not many people and not many organizations as well, right, that can celebrate 100 years. So that's the program for this morning. So let's wait a couple of minutes and then we start. Thank you. Okay, so we should start. Good morning, everyone. My name is Luis Correa. I'm with the IST, the University of Lisbon. And it's a pleasure to be here today with you as the chair for this plenary session in which, as I said just a couple of minutes ago, we'll have 2 keynotes from 2 esteemed colleagues, and also we'll celebrate 100 years of the Bell Labs, Nokia Bell Labs. So as a starting, and both Anna and Erik agree that we save the time of presenting their CVs for the Q&A and their talks. Their CVs are on the, two things actually. Their CVs are on the internet, are in the program, and they are well known. So I think they don't need a too long presentation, which actually would be too long if I'd read their CVs, right? So, Anna Tzanakaki, she's a professor at the National Kapodistrian University in Athens in Greece. So, Anna, the stage is yours. Thank you.
Thank you, Luis, for the introduction and the kind words. Many thanks for the invitation to participate in the session and give a keynote talk. It's a great pleasure and a great honor to be here. Good morning, everyone. The topic of my presentation is network security in the 6G era. I'm testing out the pointer as well. Okay. The audience here is very familiar with the introductory concepts, but I think I would spend just a moment so we all align. When we migrate from 5G to 6G, we need, first of all, to acknowledge that the development of 5G technologies is a reality around the world. However, the requirements for interconnection and performance is soon exceeding the capabilities of 5G. So 6G comes to support a large variety of applications and offer improved performance in comparison to 5G in a number of aspects: unprecedented connectivity, peak data rates, energy efficiency. What we expect from 5G is to be a ubiquitous infrastructure that integrates the most advanced heterogeneous network and compute technologies. We expect to have increased intelligence and flexibility, and this will happen through wide adoption of AI, artificial intelligence, and machine learning techniques. And then we end up with, through these points, we end up having a relatively complex or a very complex infrastructure which needs autonomous operation and self-optimization to support the performance we expect this infrastructure to support. And in addition to this, we expect 6G solutions to offer new enhanced capabilities such as localization, monitoring, and sensing of the surrounding environment. I think my cursor is not helping me anymore. Okay, now if we try to identify the technology challenges associated with this migration, I think we can clearly agree that we'll bring connectivity of billions of end devices. We have a heterogeneous cloud solution, multi-cloud, spanning from far edge to edge to central cloud. We will have the creation of millions of subnets. We have the introduction of open interfaces. We have the adoption of concepts such as disaggregation. We are moving into multi-vendor environment because we're seeing concepts and architectures like Open RAN coming into play, and of course, AI native operation, for which I heard a few times already in this conference. Okay. Now, if we all agree on the context of this discussion, I think all these new technologies bring a number of threats into play. And I think this is very important for this community to assess, to understand, and somehow address. And I made this an effort to list a few. The clear and first threat is the increase of the attack surface across all domains. We have risks which are associated with the scale of the infrastructure and the number of connected devices, and that will bring issues or challenges regarding scalability for authentication. We have physical threats. The 5G network is highly vulnerable to some physical tampering of nodes and elements. We are deploying multi-access edge computing, and this involves lightweight devices which may compromise the integrity of the devices and the data they process. We have IoT systems that the relevant data they handle are susceptible to we have IoT systems that handle a large volume of data, but they are susceptible to resource exhaustion, insecure communication, and physical intrusion due to limited computational capacity and security tools. I already mentioned the heterogeneity of the cloud environment. The far edge, central cloud infrastructures suffer interoperability challenges for security mechanisms as there is no clear relevant standardization. And if we keep on with this list, we have to worry about user interfaces. Limited user interfaces in many end devices affect threat awareness and response. We have weak computation power in specific devices, edge devices at the periphery, which will effectively lack a robust defense mechanism. We have to worry about security protocols because existing security protocols are not designed in accordance to the requirements of 6G, for example, in terms of latency or high-speed communication. And then we have to look at these cloud-native solutions that we push forward in 6G, and their concepts like, for example, an implementation, effectively, mecha containerization will introduce challenges because containers may, for example, run on compromised host, or specific containers may dishonestly consume significant resources, affecting other containers. And then we have to worry about edge security because the complexity here comes from the fact that we talk about a mobile network, so mobility of network entities across administrative domains can introduce security challenges. And going on with the list, and I think that's my last slide on the threats. There is challenges associated with concepts such as software-defined networking, decoupling of control and data planes. This can also introduce vulnerabilities. SDN switches can suffer limited memory and are vulnerable to resource saturation attacks. We have the presence of centralized controllers. This can potentially compromise network performance and integrity, and they can be overloaded and cause network disruption. So this is a risk element in the network. I mentioned already open interfaces, which in general is something positive and brings benefit, and we see this promoted by models like, for example, the Open RAN, architecture like, for example, the Open RAN. But the truth is that they expand the attack surface and expose the system to third parties. So the network is not closed anymore. We deal with the multi-vendor interoperability. That's a good thing, but it brings additional threats. Multiple vendors and service providers can lead to inconsistent security implementation and varying levels of security expertise. So this is another additional threat. And then, of course, I decided to finish my long list of threats, which is not exhaustive by no means, with the issue of AI. We can see powerful attacks. We can see adversarial attacks, which exploit vulnerabilities in AI algorithms that potentially have a very large attack surface in 6G environments. OK. I already mentioned that we have a large number of billions of end devices connected to the network, and of course this brings some issues regarding scalability of authorization and authentication. Okay, and then of course these are connected to our radio access network, and this also suffers its own network security issues. It's susceptible to physical layer attacks. There are issues with non-trusted network access. And then, of course, we have our user plane function, our UPF, which by itself suffers by other issues, security issues, replay attacks, distributed denial of service attacks. And then we have, I'm sorry, this is a little bit slow, connectivity with the edge compute, and then we have the supporting infrastructure interconnecting the different 5G elements, which is also susceptible to attacks at the compute domain, attacks at the transport network domain, and of course there are interfaces integrating the different elements together. And so if we're done with the discussion on the user plane, and if we bring it to the discussion, the control plane, then we see a very complex infrastructure that or a very complex model that you're all familiar with, service-based architecture, a large number of different virtual network functions interconnected with a number of SBIs, interfaces, and here we have the issue of attacks against SBIs, authentication and trust, attacks against microservices. So this is another set of threats that we have to worry about. And then we have to also worry about the fact that we need exposure from the different elements of our infrastructure to the external world. So we need to have secure service exposure, and the service exposure relates with how we interface our devices, the external world, the application server, for example, and the northbound interfaces to the orchestrator. Okay, so if we concentrate a little bit on the interfaces, because this is quite an important issue, then we can try to see how things happen in 5G. And in 5G, protection of SBIs commonly happens through firewall for user plane interfaces, but also for control plane interfaces. So it's quite common that we bring firewalls there, but they suffer because they are vulnerable against port scanning attacks. So okay, there is some level of security, but still can be attacked. Okay, so there is this activity, the Zero Trust Network approach, that seems to appear a very promising way forward when we talk about increased security requirements. So, and this is actually a concept with which we have been working on. So the idea here is we assume that a breach is inevitable. So there is no way that you will never have a breach. And then you can also assume that it has already occurred. So the idea is we try to limit the access only to what is needed. And then we keep on monitoring, we keep on trying to find anomalous activity everywhere. How do we do that? We apply end-to-end protection schemes through what we call local cybersecurity loops that can target the devices. The idea here is prepare, prevent, respond, and recover. And this is applied in the RAN. It's also applied, so at the end user devices, the RAN, the UPF, the edge, the core, and our service slices. So this is the methodology we apply. Sorry, there is some characters that have not been appropriately. Okay, so I'll try to give you some idea of what the zero trust architecture principles are. First of all, identity and access management. We rely on strong authentication methods. I'm not going to say a lot about authentication methods in this talk, but we rely on strong authentication methods to ensure that only authorized individuals can access applications and data. Then it relies on microsegmentation. So what it does, it basically divides the network into security domains, into secure zones that limit the movement of threats into the network. So if a threat occurs, it's isolated and it cannot compromise other devices in the network. Then we have what is called multi-factor authentication. I think the term suggests what we're talking about here. It requires users to provide multiple verification factors in order to gain access to the infrastructure, to gain access to the resources, and thus we hope that we reduce the risk of unauthorized access to our infrastructure. Then there is an element which is called policy engine. What that does is what the term also suggests. It makes decisions regarding granting access to users based on specific policies and also user behavior. So we monitor the user behavior and we can make decisions regarding whether they can be integrated or connected to the system or not. And there is what is called policy enforcement point. This brings strict enforcement of access policy. So basically, this is the facilitator to bring in the policy, the policies we want to apply. Policies consider the risk level of each transaction, and they can dynamically adjust for changing things, which can be the user behavior, user attributes, or environmental conditions, and so on. And then we have the policy administrator, which administers the policy, so establishes and terminates connections between users and resources based on policies set by the policy engine. We have the user analytics. I think that's quite intuitive what it is, right? This is responsible to analyze patterns of behavior and detect anomalies that could indicate a threat. Then we have the endpoint security. So here we have an advanced endpoint protection solution monitor that protect devices from threats. So they ensure, this endpoint ensures that only healthy and compliant devices can be connected to the network. Encryption, data encryption protects sensitive information. There is a lot of science under encryption. One can say very much. I said in this talk, I'm not going to touch upon encryption in any depth. I want to take the security from a system perspective. So my approach would be to discuss security from a system perspective. So data encryption protects sensitive information, both transing the infrastructure, but also being stored somewhere in the infrastructure, being addressed. If data is intercepted, it cannot be easily accessed without the decryption key. And of course, these principles are applied throughout the life cycle. So we have continuous monitoring and analytics. We have real-time monitoring and analysis of network traffic. We observe the user behavior. We try to detect anomalies and identify threats. This will then facilitate the response. So we try to monitor, identify threats, and facilitate fast response for risk mitigation. Okay, so these are the principles of the zero trust architecture, and here's just an example of how we can apply this. So let's assume that we have an untrusted device that you see here, and this tries to get to be connected to our resources. We have this policy enforcement point I mentioned before which will enforce the policy. There will be the key exchange needed to identify which device is this. This information will be communicated with the policy engine, which will then define the policy for this particular device, and the policy will be communicated to the policy enforcement point through the policy administrator. So that's how, in a simplified way, how it works. I know this is a very busy slide, and I apologize for this, but I will try to go through it so that I can help I can help following the concept. Okay, I'm very sorry, but my pointer doesn't help me very much. At the very bottom, you see the 5G elements that you know very well. So you see the 5G RAN, you see the transport network, you see the core network, you see the cybersecurity control loops I mentioned before. So each one of them autonomously tries to prepare, prevent, respond, and recover in case of threats. They are interconnected with interfaces we know and we discussed briefly. And then on top, we have the service layer. Again, with its own cybersecurity control loop, so we have our different service slices. And what you see at the very top is something that I haven't introduced so far. This is CTI stands for Cyber Threat Intelligence. So at the very top, we have a layer which will perform our cyber threat intelligence through a particular platform, a purposely developed platform. And what this does, it extracts information that can be communicated to stakeholders. It will create vulnerability repositories. So basically, it will monitor the infrastructure, and it will collect data relating to security. It will analyze this data, and it will then communicate conclusions to the appropriate stakeholder if we talk about teams, or to update specific repositories or trigger actions. And of course, what you see on the right-hand side of the slide is a cybersecurity orchestrator. So of course, we have a complex system. To provide any service, we need to have some orchestration across. And what I will try to do today is to say a little bit, it's not going to be exhaustive by any means, but give you a little bit of insight, at least with regards to what we have been working on possible security issues in the 6G context for the different elements of the network. So starting with the RAN. Okay, I will take the example of ORAN, of the ORAN architecture, and I show you something that I know you're all very familiar with. So we have our RUs, DUs, and CUs at the very bottom, and then we have the radio intelligence controller on top, handling near real-time control, so fast control. And we have the non-real-time RIC hosted at the SMO handling slower control. So with this in mind, let's try to see how we can handle, how we can apply zero trust networking in the RAN context. So what we have to do here is something we already talked about, implement critical control actions involving preparation, prevention, response, and recover from attacks. Of course, this involves testing system vulnerabilities before deployment. So for every system, we need to have a vulnerability test before the system can be deployed. This is actually called software bill of materials per element. I will say a little bit more about this as we go along further down. I just mentioned it here. And then protect systems as threats involve. So we have to have a dynamic mechanism to handle threats when they appear. And how do we do that? We need to take advantage of the intelligence we already have in our radio intelligence controllers. We can use our apps and XApps as the means to actually do that. So what I'll try to do now is just indicatively show you, talk about 60 use case. So one possible problem would be to have some physical layer related security issues. And this would be very relevant in an integrated, so we talk about 6G, so let's bring a 6G use case here, integrated sensing and communication. I was in a workshop the first day of the conference, and this particular point was raised, so I think it's quite relevant. It was raised as a question. So that enforced my decision to bring it in. Okay, so what we do here is we have to detect the sources of physical layer anomaly. So our system should be able to detect the source of the physical layer anomaly, and then we should be able to detect and localize jammers, fake targets, and so on that will affect our services. And now we have to worry about both communication and sensing services. Okay, so a simple example, as I say, by no means is exhaustive what I show you here, but just to give an indication of how one could do it, is, okay, this is our resource blocks, and we would like to be able to find schemes to identify attacks, physical layer attacks in this case. So one example which I found in the literature and I really liked was the fact that you can actually keep some unused resource blocks that are there for someone to be able to detect attacks. So if your system is attacked, then the pre-assigned empty resource block will not be empty anymore, right? And then how do you deal with this in a 5G system or in a 6G system? You deal by developing an XApp which can monitor the spectrum. And if you do that, you can identify the attack, and then you have to take some defense action. How can you handle defense? I can handle defense because, okay, this is my system here. You can see my beam, including my communication data. Sometime later, I will show how this can be converted into a sensing service. But for now, this is communication. And here is the attacker. I'm very sorry I cannot show you, but it appears with pink. Maybe here works better, no? No. Okay, so it appears with pink in my diagram. And then what you can do is, for example, trigger suitable there is some animation that I'm afraid I cannot bring in. Maybe I exhausted the batteries with my many animations. Sorry. Sorry. Can we do it manually from? No, okay. Okay. And then Luis will give me a little bit of a time budget, right? Okay, that's 20 minutes. It's a jam attack. You're right. You're right. The problem is I haven't found the mitigation scheme, and it's quite slow, right? So I apologize for that. So much about security. They are rebooting. Okay, let me, I don't know where it was. No, okay, but it doesn't do anything. Sorry, I destroyed the system. We were impressed this morning with all this wireless connectivity. Correct. Yes, well, resilience, no criticism, is a little bit slow, right? So, okay, I think I was, but I need to move forward, right? Yes, next one, please. Next one. Let's, please stay here. Now it's there, but let's see that it works. Okay. Okay. So we were at the point that we have discovered the attack, and we are taking measures to solve the problem. And the problem we decide to solve is, for example, use adaptive beamforming and avoid the jammer. Okay. Another way to deal with this would be, for example, to take advantage of frequency hopping. So if we identify specific, through, for example, SNR type of measurements, if we identify that there are, so these are, the purple is the used resource blocks, and if we identify that there's an attack there, what we can do is use frequency hopping and move, sorry. Okay, and move the occupation of our resource blocks elsewhere in the system, okay? Where, to resource blocks that have not been attacked. Okay, I promised I will say a little bit about sensing, so I will bring in some work that in fact we do in the concept or in the context of the European project 60 Senses. So what we do, one of the scenarios we study for sensing is to perform sensing based on the principle of distributed passive wireless radar, and then we have to consider what happens with attacks against this radar type of sensing. The transmitter and receiver can be physically separated or co-located. You can decide which architecture to take. And then the 60 base stations that you see here on the right-hand side generate communication signals, which are reflected on objects located in the surrounding area. So here you can see the object. And you can see the COM signal, and the COM signal is reflected, creating an echo, which then reaches a different base station. So the IQ echo streams are redirected then to an edge compute node for storage and processing. Okay, so what problems could we see there? We can see adversarial attacks, create additional input to machine learning models, which are designed to cause the model to misclassify or estimate wrong distances. So on purpose, try to confuse our AI model, right? And that would, for example, hide an obstacle. So the idea is that I have this system so that I can sense the environment, so identify objects and obstacles. And if that happens, then you hide the obstacles. And this can be an equivalent of dazzling the camouflage, right? Okay, I really regret bringing all this animation. Okay, so I talked about, so now we have an idea of how we can have attacks in the physical layer, and then the next thing I think of interest is to see how we can extract this information and share this information in the system and externally to our system. I think this is a very important concept for this zero trust networking approach. So we take cyber security information that can be taken from our D apps and our X apps from our radio intelligent controllers, and we need to expose vulnerabilities to what we defined in the architectural diagram before, to the cyber threat intelligence platform at the very top of this complex architectural diagram I've shown you. So this information has to be communicated and extracted there. For this, we can use specific platforms. I only bring one example here, MISP. What this does is collects, stores, distribute, and shares cybersecurity indicators and threats. So this is the way to actually, this is the means to actually expose the information. But of course, from a 5G or 6G perspective, we need to think of how we can actually do it. So which are the interfaces we are using to expose this information? Now, if this is very dependent on where the information is coming from. And if the information comes from the near real-time RIC, then we can use Y1 interface that has been defined as the interface to expose data. Or if we talk about the non-real-time RIC, which is hosted in the SMO, then we can use A1 interface. And of course, for this specific information, there are defined formats with which the information is communicated. Okay, so now, sorry, I went very fast. Now I will say a little bit about the transport network. I have personally a big interest in the transport network, and we've been doing a lot of work looking at different technologies, but focusing a lot on optical networks. So what the transport network does is supporting front haul, mid haul, and back haul connectivity, and you're all very well aware of this, and this is just a diagram to point this out. In the interest of time, I think I will go very fast across the slides, but the idea here is there are, in ORAN, there are very strict timing and synchronization requirements, and there is small tolerance in errors, and they vary whether we're talking about mid-haul or back-haul, and they become very, very tight when we talk about front-haul. So this is something we need to make sure is not compromised. So here you see different synchronization options. We can have, for example, a clock provided to the DU and RU from a common entity, or we can have different entities providing the clock to the RU and the DU. This is not so critical to discuss, of course, through navigation satellite systems. But of course, this is not so critical to discuss. What I would like to say is we can see attacks associated with the timing. So we can see attack in the form of spoofing that will impersonate a time-transmitted clock. We can see denial of service attack. We can see several things that can actually compromise synchronization. And this is a very serious problem. I'm sure the community is very, very well aware of the strict requirements we have regarding timing. So what would be the solution? The solution that has been proposed, and we see in literature, is protection of creating a synchronization plane at layer 2 and using something that is called MACsec. So implement authentication and authorization for PTP nodes and provide redundancy in open front-haul synchronization. How can we apply this? There are various deployment options. I only bring some indicative example here. So we can implement MACsec, so we create some kind of an end-to-end tunnel between the ORU and the ODU, or we may decide to create a similar tunnel, but now between the edge transport network elements. So specifically targeting the transport network itself. Okay, and then it was the core network that I wanted to talk about. What is the issue here? The issue here is that we have a large attack surface. We've seen the architecture before, large number of virtual network functions interconnected with SBIs. So we have multiple interfaces interconnecting virtual network functions. We have an open system architecture that enables massive device connectivity, and we can have compromised UEs, which can cause significant damage to the system. What does the zero trust network approach does? It brings the concept of a message broker. This broker brokers connections between components of the system. It creates connectors which are deployed in front of the microservices we want to support, and then creates, again, secure tunnels. So we bring the concept of tunneling again here between the different VNFs to support security, and effectively we create what we call the zero trust message broker. Okay. The tunnels are created, and then we can apply different policies. So if a UE is secure, then we can, is not introducing vulnerabilities. We allow the service, the end-to-end service. If we discover that there is some level of vulnerability, then we can adopt this segmentation, micro-segmentation approach I talked about, which basically isolates the element creating the issue, and also performing deep packet inspection to identify what the issue is using specific tools. And I'm only mentioning ABF here as an example. Okay. So if we have, in the context of the discussion before, a UE that is a normal UE causing no security threat, then it goes through the different elements, and the connection is established. This tool I was referring to before that is able to give us the deep packet inspection resides at the user plane function, and what we do is we have our connections going through Okay, we have our connections going through this element. Safe UEs are connected properly. If we identify a threat, then alerts can be triggered, and then we can trigger mitigation policies, so we can set the UE in an inactive state. Okay, and going now to the services. When we talked about the architecture, we had this service slice, service slices over the actual infrastructure, 5G infrastructure. And what we show here is an attack scenario. So we have a slice service that is provided, say, through the infrastructure that you see here. And then at some point in time, an attack is detected. How do we react to this? We bring resilience, hopefully fast. And then what we do is we go through an alternative module, alternative compared to the one that we have identified the attack to reside at. Okay, and then of course we go to the hot topic of this and many other conferences, AI. AI models providing intelligence they provide intelligence for the operation of our network, and that involves, of course, the mobile elements and the network infrastructure, so RAN, transport, core network. And what we have to do is use this intelligence to also provide network slices and effectively provide end-to-end services through our end-to-end orchestrator. So there are different levels of AI elements embedded into the system, and I think this is partly the discussion of native AI in the context of 6G. AI models, in general, are deployed hierarchically, and training and inference of AI models can be performed at different locations of the network. So here you see on your left-hand side, you see the hierarchical structure where we can have training and inference of the different AI models. Now, AI is brought into our system to bring intelligence. And the question is, to handle intelligence, we need knowledge. And the question we need to pose to ourselves is how we manage the knowledge. In fact, there are two ways. If we try to generically classify how we manage knowledge, there are two ways to actually do it, either in a centralized way or a distributed way. And if we do it in a centralized way, what happens is we have data collection and processing, collecting measurements from multiple elements in the network. These are collected and stored in a central location. And then what we do is, based on the full data set we have, our machine learning models are trained, and they can make predictions for all building blocks of the system, taking this centralized approach, right? So we have this one element containing all the data. And then the trained models are deployed in the system and executed, right? So we have the inference at this one location. So the alternative approach is to apply distributed knowledge management. And one technique that I'm sure you have come across is federated learning. We have been doing some work with federated learning over the years. Okay, so the measurements are stored locally. It's a distributed approach. Based on the local data set, each element trains a machine learning model for a specific time duration. Locally trained machine learning models are transmitted to a centralized server, which aggregates the received models, creating a new machine learning model. Now, this new machine learning model, I will jump my animation very fast. This new machine learning model is communicated again to all the individual elements collecting data and keeping their own machine learning models, is compared to this, and they are updated accordingly. And the process keeps on going until we reach a certain level of accuracy, which is acceptable for a system. Okay. Machine learning threats. What are the possible threats? The possible threats would be data, okay, that's not very good. Data poisoning. Basically, we can have data inserted, modifying our data, affecting the training of our system. We can have a machine learning model poisoning, where we can affect the parameters of the model, and we can have a machine learning inference attack, where we can extract information from training data and find out information about about our system. Okay, one way to handle this, and I will say this very fast, is conventionally, when we implement federated learning, what we do is we send data, as I showed before, from distributed entities to a centralized server and exchange information backwards and forward. And the issue of security is the fact that we can send this data, but every time the central server needs to process them, if they are encrypted, they need to be decrypted and processed and then encrypted again. The issue that arises is what happens if we don't trust the central server. Okay, an approach that's been proposed in the literature is what is known as homomorphic encryption, which basically relies on the fact that there have been discovered ways to actually do processing of data, do addition, multiplication, and so on, of encrypted data. So when you reach your central server, you don't need to decrypt. You can handle encrypted data, and that will be actually a very safe way to do that. So I had all this in a more detailed way to show to you. I said a little bit about information sharing. This is something we need to keep in mind. I'm not going to spend more time on this. I've already given you an idea. This is the software bill of materials I was taking you about, which has to do with scanning elements that we will integrate into the network to get their security profile. All this information has to be communicated, but it has to happen securely, so we use the secure edge proxy concept. And the last thing I want to say, if Luis, give me one moment, is there is relevant activity in the legislation activity in the EU. The relevant, the points I would like to make is this referred to the Cyber Security Resilience Act, which has to do with ensuring that manufacturers improve security of products with digital elements. I'm not going to go into the details. You can find the relevant literature. It's openly available. But I think the important point to make is the CRA entered into force on December 2024, and the obligation will apply in 2027. So it's coming up. And there's also the NIS2, Network Information System Directive, which requires adoption of technologies to implement full-range DevSecOps. Here I have some of the requirements it brings. But again, I would like to say that since October 2024, NIS2 has been a legal security requirement through the EU states. So this is everything for me. Probably, do I have time for conclusions? Maybe 30 seconds, okay. Okay, we talked about the benefits of 6G, but when we look into the technologies we have to bring together, I think all agree that there are significant challenges in terms of security. We have to deal with security in 6G in an organized and well-defined framework. We have been working with the zero trust networking approach, so we think it gives a really a relevant and nice framework to work with. In this context, a variety of threats can be identified, and then they can be addressed to minimize occurrence, but also impact. It's important to share information across entities, relevant entities and stakeholders. And of course, there is relevant EU legislation. There is no way to live with zero attacks. We heard this as a conclusion from a panel yesterday. I would totally agree with this, but we need to take measures to handle attacks. So that's everything from me. Thank you very much. Okay, I'll leave this.
So the floor is open for questions. I don't know if there, yes, please. Please present yourself.
Yes, Emmanuel Lotaro from Thales. You mentioned at the beginning of your talk, and I agree, that we are lacking some standards in security, and not only for CTI, but to make it operational end-to-end. So my question is very simple. What should be the standard body of choice to make those standards?
Okay, that's a very nice question. What I can say, I cannot really express a choice. I think it really depends on what architectural approach and technologies are adopted. What I can give you as an insight is that there are currently activities, standardization activities on security on 3GPP and ORAN. And in fact, in particular, ORAN, they published a large number of security-related standardization documentation very recently, in February 2025. So there is activity, but I obviously cannot indicate what's the best way
I said
forward.
end-to-end, so I'm not sure that ORAN will cover end-to-end issues.
Okay, you're right, you're right. Not necessarily end-to-end issues, but there is activity. So NIST, this zero trust approach is proposed by NIST, so US counterpart. So I think we need to evaluate options here. But yes, I agree with you. The end-to-end side, so the equivalent of the zero trust, we couldn't really find defined in the standards. That's why we had to look at alternative options.
Okay, Anna will be around during the coffee breaks. I think we can save the rest of the questions. You can interact directly with Anna. So just as a show of our appreciation. Thank you very much for your talk.
Thank you very much, please. Thank you. Okay. Thank you. Thank you. Thank you very much. Thank you.
So the next speaker is Erik Ström from Chalmers University, an old friend for many years as well. I don't know.
Yes. Okay. So thank you so much, Luis. And all right. So it's been a long morning. So I would be a little bit awkward here and just ask you to raise up and shake off a little bit of the dizziness. So, raise up, come on. It's awkward. I know. Let's do this. And let's shake loose a little bit. Okay. All right. So now we're ready. Okay. So I will talk, and thank you for inviting me to give this talk. So you're going to allow me to talk about a few things that I really care about, research and also this issue about machine-type communications. So first of all, there is an elephant in the room that I think we should talk about. We also need to talk a little bit about the role of academic and industrial research. What are our roles really here? And after this, high-level things, I would like you to take your journey down a rabbit hole. And that rabbit hole has to do with machine-type communications, in particular, short block-length machine-type communications. Okay, but let's start with the elephant in the room. okay? There's a big elephant in this room, and it's like this. Right. So there is 5 years before 6G is deployed, but it's time to talk about 7G. Right. Do we need it? Of course. 6G will not be perfect. Right. So there is room for improvement. And every now and then, we need a network to be, of course, obviously, we always need to build a network, to build new capabilities, to meet new and old challenges. We have done that for ages, right? That's nothing new. We also need a new generation every now and then when we need to break the curse of backwards compatibility, right? And that happens every now and then. So that's why we need 7G. And for your academics here in the room, it's about time to start to think about what is 7G. Okay. Inspired a little bit what Matti said yesterday, think early and think fast, because soon it's time for the next generation to go into, you know, the regular cycle of EU projects, standardization, and so forth. Okay. Now, the role of academic and industrial research, what is that? Well, here's a very oversimplified model, but it has a little bit of a grain of truth, at least I think so. So the role of academic researchers is to propose and study crazy stuff. Okay, that's what we need to do. The industrial researchers should evaluate this crazy stuff and discard it or make it viable. All right, it's important that both of these roles are fulfilled. Okay, we need crazy stuff. We need to explore new things to see what are the gains. And we also need people to do the fact check. You know, does this really fit? How are we going to make this work in practice? It's important also that the same person can step into both of these roles. And I think as an academic, we're privileged because we can be on the left-hand side without our employer firing us, right? So we should take that